Okay, at this time we're going to go ahead and do Heat Pump Diagnostic Module 1. And if you'll please look at the screen and the recording. We are recording this session today. And so by all means, if you were participating on the live session, you would be recorded. So please keep that in mind when we do our live training today. So welcome to the program. Today we're going to be covering some very important material. And some of that today will be as follows. We're going to overview the refrigeration cycle for a heat pump. We're going to talk about reversing valve operation and gas flow for heating and cooling modes. We're going to discuss the expansion valve, also known as a TXV. We'll overview that. We're going to be talking about check valves and their function in the heat pump refrigeration cycle or circuit. And we're going to be talking about bi-flow metering circuits and how they're used in a heat pump refrigeration cycle. So the first thing we're going to talk about today is going to be our refrigeration cycle in the cooling mode. So as we take a look at our diagnostic screen and the graphic, you'll notice that starting at the compressor, we have a hot gas line coming from the compressor into the single line into the reversing valve. Now remember, team, when we're in the cooling mode of operation, the outdoor coil is a condenser and the indoor coil is acting like an evaporator. You'll also notice that on the screen that the outdoor coil in the cooling mode will be color-coded red or a bright pink, indicating it's hot gas going into that coil. You'll also notice that on the indoor evaporator in the cooling mode of operation, the coil is color-coded blue, indicating it's cold or cool. So from the compressor, we have hot gas from the compressor to the single line on the reversing valve, and in the cooling mode of operation, we divert that hot gas to the outdoor coil that's acting like a condenser. We then come out of the outdoor coil through a bi-flow TXV, and remember, team, in the bi-flow configuration, in the cooling mode of operation, the bi-flow TXV outside has to flow that refrigerant out of that coil freely, that liquid refrigerant. So we have liquid refrigerant going through the bi-flow TXV in the cooling mode on the outdoor bi-flow TXV. We go through a bi-flow filter dryer down the liquid line to our bi-flow TXV on the indoor coil. Now remember, in the cooling mode of operation, the bi-flow TXV should be metering refrigerant into the cold coil, and it is, and we see that as being a blue color code. We then meter refrigerant into the indoor coil where it boils off and absorbs heat from the air passing over the coil and changes state into a cool vapor. That cool vapor then travels down the indoor coil vapor line back to the reversing valve where it loops through the reversing valve back to the common suction line on the compressor. Now you'll also notice that right in the middle of your screen there's going to be a suction gauge and a discharge gauge. You'll notice that the suction PSIG will be displayed in pounds per square inch gauge, and the discharge PSIG will be pounds per square inch gauge. You'll also notice that the suction gauge is blue in color, and the reason that is because on your actual manifold set that the technician will use in the field, the blue colored gauge is going to be, or the blue housed gauge will be the suction gauge, and the red housed gauge will be the discharge gauge. Now team, I'd also like you to notice something, that the background of the gauges on the graphics today. The background is white. So if you have a white background on our refrigeration cycle diagnostic screen, if you have a white background on the gauges, you automatically know it's an R22 call. If it has a pink or rose-colored background, you automatically know it's a 410A call. So that'll be a little visual cue moving forward when we're looking at the graphics. We know that it would be an R22 or a 410A call based on the color of the background of the gauges. So again, in the refrigeration cycle cooling mode review, we see we've got hot gas going to the outdoor coil and cool gas coming from the indoor coil in the cooling mode. At this time, let's go ahead and review the refrigeration cycle in the heating mode. Now remember, team, the heat pump is able to heat and cool the conditioned space with the refrigeration cycle. And the way we do that in the heating mode of operation, we take the hot gas from the compressor and we divert it through the reversing valve to the indoor coil. Now remember, in the heating mode of operation, the indoor coil acts like a condenser. So that hot gas goes to the indoor coil where we reject heat from that indoor coil into the conditioned space in the heating mode. We condense that hot gas into a liquid, and we go through the biflow TXV on the indoor coil. Now remember, the biflow TXV has the capability of allowing refrigerant to flow freely in one direction and meter refrigerant in the other direction when that coil is acting like a cold coil or an evaporator. So in this case, in the heating mode of operation, we have hot gas from the compressor going to the indoor coil that's acting like a condenser in the heating mode. We then flow that liquid freely out of the indoor coil that's acting like a condenser through the biflow TXV check valve circuit and down the liquid line in the opposite direction of the cooling mode. We then pass that liquid through the biflow filter dryer. We then go into the biflow TXV on the outdoor coil, which is now acting like an expansion valve. It's metering, so it's metering refrigerant into the outdoor coil that's actually going to be cold or acting like an evaporator in the heating mode. We then boil that refrigerant off in that cold coil outside as we absorb heat from the outdoor air. And then that cool vapor from the outdoor coil goes back to the reversing valve, where it loops back through the reversing valve and the common suction of the compressor. Now it should be noted that in the heating and cooling mode of operation, the main thing we have to keep in mind with a heat pump is the reversing valve that's diverting hot gas to the indoor coil in the heating mode and the hot gas to the outdoor coil in the cooling mode. This is very, very important. You'll also notice on your refrigeration cycle graphic there's going to be some arrows. Those arrows will kind of help you visually see which way the direction of refrigerant flow is. So as the arrow, in our example, the bottom arrow is pumping hot gas towards the indoor coil, and the liquid is pumping back towards the outdoor coil in the heating mode of operation. And again, team, remember, right in the middle of the screen, you're going to have a suction gauge and a discharge gauge. And if those gauges have a white background, that automatically tells you this is an R22 call. If it has a pink or rose-colored background, you'll notice that that's a 410A call. So the next thing we're going to talk about specifically is the reversing valve. Now, we spoke briefly when we looked at our cooling cycle and heating cycle review that we had hot gas coming into the reversing valve. Well, this is just another little picture of the reversing valve, and we see the top graphic in the cooling mode of operation. We have hot gas coming into the top of the valve, and then it's going to be diverted to the outdoor coil. And in the cooling mode of operation, we have cool gas coming from the indoor coil, looping through the reversing valve back to the compressor suction. In the heating mode of operation, we shift that reversing valve, and now we have hot gas from that single hot gas line from the compressor going to the indoor coil that's acting like a condenser. And then the outdoor coil is acting like an evaporator, so we have cool gas coming back from the outdoor coil, looping back through the reversing valve back to the compressor suction line. So as we take a look at the reversing valve a little closer in this graphic, we see that the reversing valve is responsible for diverting hot gas either to the outdoor coil in the cooling mode or the indoor coil for the heating mode. And this is how we achieve heating and cooling operation on the heat pump. A very, very important device in the heat pump is an expansion valve or some sort of metering device to meter refrigerant into the cold coil. Now, team, at this time we're going to stop using the verbiage of evaporator and condenser because we found out in our review here a little while ago that it doesn't really matter which coil is acting like a condenser or which coil is acting like an evaporator, in the fact that in the cooling mode of operation, the outdoor coil is warm and the indoor coil is cold, and in the heating mode of operation, the indoor coil is hot or warm and the outdoor coil is cold. So we see that when we're metering refrigerant into either the indoor or the outdoor coil, one of those coils are going to be cold when it's acting like an evaporator. So from this point on, we'll talk about the cold coil when we're metering refrigerant into it with the expansion valve. So if we take a look at the expansion valve closer, we see if we follow the liquid line, we see the liquid line is actually feeding refrigerant through the expansion valve assembly, and it's going to feed refrigerant into the cold coil. Now at the outlet of the cold coil, you'll notice there's a sensing bulb. That sensing bulb is clamped onto the cold suction line or the cool vapor line leaving the cold coil, and inside that sensing bulb there's actually a refrigerant. That refrigerant, when it starts to warm up inside that sensing bulb, will exert pressure on top of the diaphragm of the expansion valve, also called the TXV, and it will drive the valve open against spring tension. As we drive that valve open, we'll actually add more refrigerant into the cold coil. As we add more refrigerant into the cold coil, it'll start cooling down some. As we start cooling that coil down, the sensing bulb at the outlet of that coil will also cool down, and it'll ease up the pressure on top of that diaphragm. As we ease the pressure up on the diaphragm, the spring will start closing the valve off. As we start closing the valve off, we'll have less refrigerant going into the cold coil, and the coil will start warming up again. As we warm the coil up, the sensing bulb will exert more pressure on top of the diaphragm. We'll start driving the valve open. So back and forth, based on the temperature of that sensing bulb at the outlet of the cold coil, back and forth, that expansion valve, also called a TXV, will modulate or meter refrigerant into that cold coil based on the amount of heat energy that's actually going across that coil from the air passing over that coil. So the expansion valve has a very, very unique capability of opening and closing and maintaining a constant and optimal flow rate of refrigerant into the cold coil. Now, one of the things that can happen with an expansion valve is if we do not have some method of buffering that action in the expansion valve, it can get a little bit erratic in the fact that the spring tension is trying to close the valve off and sensing bulb pressure on top of the diaphragm is trying to open the valve. So those two mechanical forces kind of fight each other. Well, to help buffer or to help stabilize that mechanical action, what we're going to do, we're going to take suction pressure from the outlet of the cold coil on the external equalizer line. That suction pressure from the outlet of the cold coil along that external equalizer line will provide suction pressure to the underside of the diaphragm. If you look at the graphic closely, you'll see that you're going to have suction pressure off the suction line or the vapor line up from the cold coil, and that suction pressure will be to the underside of the diaphragm. That's a balancing and buffering force. So the external equalized expansion valve is going to have that buffering force with the suction pressure on the underside of the diaphragm. Now this is really, really important. That external equalizer line is not there to equalize pressures in the system when the compressor shuts off. That's a common misconception in our trade. The external equalizer line, the sole purpose of it is to take suction pressure from the suction line or the vapor line leaving the cold coil and putting suction pressure to the underside of the diaphragm as a smoothing, buffering, and stabilizing force. That's what it's there for. So let's go ahead and move on then. We've talked about the expansion valve and its function to meter refrigerant into the cold coil. One last final note on expansion valves. There's a special type of expansion valve called a bi-flow expansion valve or TXV that has a check valve built into it so that in one direction, when the liquid line is coming into the expansion valve and it needs to be metered into the cold coil, it'll do as we've just described in this session. However, when that cold coil becomes a warm coil or a hot coil, in other words, it's acting like a condenser on a heat pump, that liquid refrigerant has to flow back in the other direction freely through that bi-flow TXV. So a bi-flow TXV is a specially designed expansion valve that has a check valve circuit in it that allows the refrigerant to flow, the liquid refrigerant to flow backwards through it freely. And so in this graphic, we see the expansion valve is being used to meter refrigerant into the cold coil. But please remember, on a bi-flow TXV, it works exactly the same, metering refrigerant into the cold coil. However, when we go into reverse cycle, for instance, like on a heat pump, we have to be able to flow that refrigerant in the opposite direction freely. And that's what the bi-flow TXV will allow us to do. The next thing we're going to talk about in our heat pump module 1 today is check valves. You're going to have some sort of check valve in the refrigerant circuit, in the liquid refrigerant circuit on a heat pump in order for it to operate in both heating and cooling mode. We achieve that with a device called a check valve. Now the check valve is very, very simple. We see in the top graphic. In the top graphic we see that refrigerant is actually blocked when the ball of the check valve is pressed against the seat inside the check valve. However, if we reverse the flow on that check valve, we see that we have free flow as we dislodge or we move that ball from the seat of that check valve assembly. So a check valve is very simple. It's a very simple device that blocks refrigerant flow in one direction, but when refrigerant is flowing in the opposite direction, it allows it to flow freely. This is a key point we need to remember. Check valves are an integral part of a heat pump refrigeration circuit. If we take a check valve and an expansion valve and put them together into an assembly called a bi-flow metering circuit, what we then have on a heat pump is we now have a circuit that in one direction we're going to meter refrigerant into the coil when it's acting like a cold coil. However, in the opposite direction, in the opposite mode of operation, when that coil is acting like a warm coil or a condenser, we allow that refrigerant to flow freely out of that coil. So in our graphic, we see that we have, in our particular graphic or drawing, we have a TXV with a check valve that's actually piped around the TXV in our graphic. However, we remembered, or we learned earlier, we also have a device called a bi-flow TXV. So the bi-flow metering circuit can be a check valve and a TXV as two separate components, or it can be a bi-flow TXV where the check valve is actually built in to the TXV or expansion valve, or it could also be an orifice or a piston type of metering device. Any three of those combinations, check valve with a separate TXV, or a bi-flow TXV where the check valve is built inside, or the orifice or piston assembly, they all work the same. In one direction, they meter refrigerant into the coil when it's a cold coil, and in the opposite mode of operation, when that coil is warm and acting like a condenser, it unseats that check valve assembly and allows that liquid to flow freely in the other direction. Okay, at this time, let's go ahead and jump into our heat pump diagnostic module 2. And again, we'd like to welcome you to this portion of the program where we will be discussing variable speed air handler control boards. In addition, we're going to be looking at all the inputs and outputs of the control. And this is a skill every technician needs. So please follow along as we discuss the following key points. We're going to talk about low voltage inputs and outputs on that control board. We're going to touch on the communication bus and terminals, a humidifier and electronic air cleaner outputs, heating, delay, cool, and adjust jumpers on this variable speed air handler. Now it should be noted, team, the reason we selected the variable speed air handler is it's because it's the most complex air handler as far as low voltage wiring is concerned. If you can wrap your head around how this wires, you can literally wire anything in our inventory on our residential indoor products. So let's go ahead and review this at this time. We'll go over every input and output on the board as we talk about the variable speed air handler control. So please take your handout that shows this picture of your variable speed control board. We're going to ask that you follow along with each input and each output. Now it should be noted, let me make a qualifier. It should be noted this board is not going to come from the factory with all of the wires off the board. We've removed all the harnessing off the board so that it's easy to look at on our PowerPoint presentation today. So it should be noted this board will have some harnessing from the factory and some pigtails from the factory to where you'll actually hook up your thermostat. But we've taken all that harnessing off so that we can look at the board easily on our handout and on our PowerPoint presentation today. So please take your handout or your workbook and find the page that has the air handler control board variable speed, and please follow along and make notes on that page as we go through all the inputs and the outputs on the variable speed board for your education today. So starting on the left-hand side, it should be noted that this variable speed air handler board is communicating capable. And you'll notice that there's going to be a service tool input as well as an A, R, C, and B. The A, R, C, and B will be your 4-wire communicating wires from your communicating thermostat on the wall down to those 4 terminals A, R, C, B. And then you'll take those same 4 wires outside if you have a communicating outdoor unit. Now it should be noted the communicating system is a 4-wire communicating system, and it's a Johnson Controls Champion exclusive protocol on that communicating. You can't use another manufacturer's communicating thermostat, in other words. So make sure you've got your hex thermostat or the appropriate communicating thermostat from Champion, Johnson Controls, A, R, C, and B. And this is where you'll actually hook it up if you go communicating. If you elect not to go communicating, that's okay. We'll discuss in a little bit how you can hook this board up for a standard 24-volt hookup with your favorite heat pump thermostat. So the board is very, very versatile. It's one of the things I really like about our Champion product. In this case, we have a variable speed, a fully variable speed indoor air handler that has the capability of being communicating or conventional 24-volt wiring. Very, very nice, versatile board. So as we move around the board, at the top of the board, we'll see that we've got some leaving air sensor terminals, LAS, which is optional. And so if you have a communicating system and you desire an additional leaving air sensor, you can certainly have that on a communicating system. In addition, you have a FLT or float switch, which is again, communicating thermostat optional function. You have a HUME output. Now it should be noted this HUME output will work either with communicating or 24 volt, either one. It's a 24 volt AC output to power a humidifier if so desired in the heating mode of operation. Right next to the HUME output, you have two terminals that are called EAC. The EAC terminals are for electronic air cleaner. Now it should be noted, unlike the furnace product, the electronic air cleaner output on the air handler is 24 volt output, and it will provide a 24 volt output on the EAC terminals anytime the fan is running. As we move around the board, we see we have a CFM light. That CFM light is a real nice, convenient visual cue on the CFM that the motor is programmed for. So on any function that we have on the board, if we're calling for 400 CFM or 800 CFM or whatever the case may be, that light will illuminate one time for every 100 CFM. Now team, please write this down and put this in your memory. We always want to size and we always want to establish our airflow for 400 CFM per ton of cooling. So we always size our ductwork and we always size our air handler and we set our airflow up for 400 CFM per ton of cooling. So to give an example, if we have a 2-ton unit outside, we're going to need 800 CFM and that light would blink 8 times for a cooling mode of operation. If we have a 3-ton unit outside, we need 1200 CFM. Remember team, 400 CFM per ton. And so the CFM light will give you a visual indicator of the CFM that you're actually moving once you set the board up. So the CFM light, again, a very, very handy little visual cue. But remember, we always set our ductwork up, we always design our ductwork, and we always set our airflow up for 400 CFM per ton of cooling capacity of the outdoor unit. Next to the CFM light, we have a status LED. And this status LED will actually generate fault codes for us that we can look at. It should be noted, please note, that normal operation is 2 seconds on, 2 seconds off, 2 seconds on, 2 seconds off, and so on. So the normal flash is a 2-second on-off sequence. Because we have a variable speed air handler, we're going to have some heating airflow jumpers. Now please notice the airflow jumper A, B, C, D on the heating airflow jumper and look at the install information to determine how much heating airflow you need. Now team, this is really important that you do this because based on your heat strip size, again based on the size of the heat strip that you've selected, will determine where your heating airflow needs to be. So please look at the install information for more details. The cooling airflow jumper is going to be found again in the install information, and you'll be utilizing the cool and adjust jumper together. Now please make a note of this or write this down. The cool and the adjust jumper work together. The cool and the adjust jumper work together to provide cooling airflow. So it's very, very important. Look at your install information, and based on the size of the outdoor unit, will be determined where you put your cool and adjust jumper for the tonnage of the outdoor unit. Now remember team, 400 CFM per ton is where we're going to adjust our cool and adjust jumper for our cooling airflow. The last jumper that we're going to talk about is, with our airflow jumper, is our delay jumper, the delay jumper. The delay jumper, please look at the install information. The delay jumper will allow us to set up airflow based on geography. And you'll notice there's 4 jumpers, A, B, C, and D. And so that A, B, C, and D will be, you'll be able to set up the delay jumper, cooling delay for a humid environment, a dry environment, a temperate environment, or what we call normal environment. And so it comes from the factory in the A normal position, and it should be noted that B is humid, and so on. So look at the install information for more details as to where you want to set the cooling delay jumper. Now, team, remember, based on geography, you may want to have slower airflow to wring the extra moisture out of the air anytime you get a call for cooling. That's what the delay jumper does for you. It's a ramping profile that allows the fan to start out slowly in the cooling mode of operation and then ramp up to a higher airflow and then finally ramp up to 100% airflow based on the jumper setting that you've selected on the delay jumping. Again, please look at install information for more details on where to set the delay jumper if you have a humid or a dry environment in your geography. The next jumper we're going to talk about is what we call humidistat. If you're going to have a humidistat hooked up to the board, you want to make sure and put that in the yes position, because the yes position will enable the board to look for a humidistat. Now, it should be noted that on your low voltage wiring, if you have a 24 volt hookup, the HUME wire will be a purple wire on our low voltage hookup. And we'll talk about that low voltage hookup later. But please remember the humidistat jumper has to be configured to tell the board if you're going to use a humidistat, yes or no. Now, please write this down. This is really important. In the cooling mode of operation, if you're going to use the humidistat in the yes position in the cooling mode of operation, you have to have a humidistat on the purple HUME terminal. Because if you do not have a humidistat on the purple wire and the humidistat is in the yes position, what it will do, it'll reduce the airflow to 85% airflow, and it'll stay at 85% airflow unless it sees an input on the purple HUME wire. So when in doubt, if you're not going to use the humidistat enable function, or you're not going to use the humidistat cooling function, then be sure that humidistat is in the no position if you don't want to use it. If you are going to use it, please write this down. If you're going to use the humidistat yes jumper, down below on our HUME purple wire, it has to have a humidistat on it. Otherwise, you will never get above 85% cooling airflow. Next to the humidistat yes-no jumper is going to be an additional jumper called AC or heat pump. If you look closely, you see that jumper, you can't really see the A on the AC, but what that jumper is for AC or heat pump. And what that does, you're going to configure the air handler for either straight air conditioning, AC, or heat pump operation. Now, it comes from the factory in the AC position. So remember, team, if you're going to put it on a heat pump, you have to move this jumper to HP for heat pump operation. And what that does, that enables the board to look for the O terminal. Let me say that again. When the HP jumper is in the selected position of HP, it's going to look for the O signal on the low voltage terminal. If you're using a standard 24 volt operation, it's going to look for O signal to enable the heat pump in the cooling mode. So please write that down or make a note of that on our Champion heat pumps, we energize the reversing valve in the cooling mode of operation. Now remember, team, if you hook this up communicating with your 4-wire communicating, you won't have to configure all that, because the communicating system will automatically configure the board for heat pump or straight cooling for you. So it's important that we understand that if we hook up 24 volt, if we use a standard 24 volt thermostat, we have to tell the board certain things, and one of them is it on a heat pump or AC unit. And again, if you do go communicating with a 4-wire communicating, as soon as you hook the communicating system up, It'll configure itself for heat pump or AC. So that's one of the great advantages from an install standpoint of using communicating. It's very, very simple, and it's essentially plug and play compared to moving all these jumpers and so on that we've talked about with standard 24 volt. But because of the versatility that we engineer into this board, if you want to use a standard heat pump thermostat and not go communicating, that's perfectly fine as well. But please remember, you're going to have to set up your cooling airflow, your heating airflow, your delay profile, your humidistat, yes or no. You're going to have to set up your board to tell if it's on a heat pump or straight cooling, which is perfectly fine. Don't forget to do that if you go 24 volt conventional wiring. As we move down the board, you'll see there's a plug called model plug. And what that is, that's a model ID plug. It's a simple wired plug that tells the board what size air handler it's hooked up to. So please remember, this model ID plug must be on the board for the board to function. Now it should be noted that if you have a replacement board, if you replace a board on an air handler, you have to take the model ID plug off the old board and snap it onto the new board. So please, if you're coaching your contractors and you're talking to your contractors, or you sell your contractors a new variable speed air handler board, be sure and coach them on that. To take the model ID plug off the old board and snap it on the new board. That way, when you power the new board up, the replacement board, it'll look at that model ID plug and it will automatically know what size air handler that it's hooked up to. So the model ID plug is important to be on that board. As we look in the lower left-hand corner of the board, we see there's a 3 amp fuse. This 3 amp fuse is designed to provide 24 volt protection to the board and the 24 volt components. You'll also notice that it comes from the factory with the 3 amp fuse. So by all means, make sure that we coach our contractors not to put a 10 amp or a 6 amp fuse in there. Typically, we can go up to 5 amp, but it'll be silk screened on the board if it allows that. If it does not say 5 amp maximum, then by all means be sure and coach our contractors when you talk to them to replace that. If they have to replace that fuse, find out why it opened that fuse and then replace it with a 3 amp fuse. Next to the fuse, we have a blower and heat strip harness. Now team, this is harnessed in from the factory. You don't have to configure this or move anything with this. This is all harnessed in from the factory, and when the blower and the heat strip harness is plugged in, there will be wires that will go down to the appropriate harnessing based on the size of the heat strip that you put in. But this is something that, again, you do not have to configure. This is already configured on the board from the factory. We've just removed that harnessing in the photo so that we could talk about the board. Next to that is our thermostat connections. Now remember, team, you're only going to go either 24 volt or communicating. You're not going to try to hook it up both. And so if you decide not to go communicating with our 4-wire communicating terminals that we talked about earlier, if you're not going to go communicating, then you're going to be hooking the board up with a standard 24 volt thermostat connection. Now it should be noted that on this harness, it terminates with a 6-inch and approximate 6-inch pigtail. So there's going to be pigtails on this air handler control board. From the factory, there'll be a harness that comes out and it'll give you about a 6 to 8 inch pigtail to hook up your thermostat. So those thermostat connections, or those thermostat pigtails or wires, is where the contractor will come down from the thermostat and hook up to the air handler for conventional 24 volt wiring. Now at this time, we're going to go ahead and blow that photo up a little bit of that section so that we can talk about each wire, each 24 volt wire separately. And so at this time, let's go ahead and blow that up in the next slide. And as we take a look at the next slide, we see that we're going to have harnessing hooked up here. But more specifically, let's talk about what each one of those wires will do. So starting at the left-hand side, the R terminal, or the R wire, is our 24 volt hot that'll go up to the thermostat and provide that R, or 24 volt hot wire. That's a red wire. Next to him is a G wire. The G terminal is our fan on command, And so up to the thermostat or coming back from the thermostat, we'll have a green wire coming to this G terminal or this green wire for fan operation. Next to that is our Y/Y2 input, and this is a yellow wire, and it's to command 100% airflow. Now the team, this is very, very important. On the variable speed product, we start thinking about our airflow more so than just off and on. On a variable speed product, we're going to think about airflow in percentage of airflow. So in other words, if I get a 24 volt signal from the thermostat on this yellow wire, it's going to drive the variable speed fan to 100% cooling airflow. Right next to the Y/Y2 yellow wire is going to be a yellow and black wire called Y1 input. So the Y1 input, if I get a call from the thermostat for Y1, let's say we had a 2-stage product outside, and I got a Y1 call or a 24 volt signal from the thermostat on Y1 on this yellow and black wire, it's going to drive the fan to 65% of cooling airflow. So now the obvious question comes, well, what if I have a Y1 and a Y2 call together from the thermostat calling for high-speed operation on a 2-stage product? Where would the fan go? Now please write this down, or please remember this, team. On every variable speed product that we have in our champion lineup, whether it's an air handler or a variable speed furnace, if the board receives more than one airflow command, it always drives the fan to the highest command that it's receiving. Let me say it again. If you have more than one airflow command on the variable speed control board, for instance, in our example, Y1 and Y2 together, first stage, second stage airflow command together for cooling, it will always drive the airflow to the highest command that it receives. Now, it should be noted, team, remember, this board is actually heat pump compatible. So if we had a Y1 and a Y2 call on a heat pump, a 2-stage heat pump, and then we added an auxiliary heat call, W1 or W2, then what's going to happen? You're going to have 4 commands on that board at one time. W1, W2, Y1, Y2, and so on. Remember, it doesn't matter how many commands you have on the control board from the thermostat for airflow, it will always select the one that's the highest command that it's receiving. So even if you have multiple commands, this is an important concept with variable speed products. So even if you have multiple commands on the board from the thermostat for different staging operation, first stage, second stage heating, first stage, second stage cooling, and so on, it will always drive it to the highest command. Now please remember, team, if you have a single stage air conditioner outside or a single stage heat pump outside, you would only use the Y/Y2 for your cooling call. You would not use Y1 for a single stage unit outside. Because remember, team, a Y1 input all by itself on the board is going to only give you 65% airflow. So if you have a single stage heat pump outside or a single stage air conditioning unit outside, you want to make sure and use the Y/Y2, because we learned a minute ago that that's 100% airflow, and that's correct. You want full airflow on a single stage unit. So the only time you'd use a Y1, or that black and yellow wire, is on a 2-stage product for first stage airflow for cooling, 65% airflow. Right next to that terminal is W2, which is a brown wire. That's our second stage heating airflow for auxiliary heat. W1 is our first stage heating airflow with auxiliary heat, and that's a white wire. Now team, remember we talked about that heat pump and AC jumper up above on the board earlier. Well, remember when we put it on the HP or heat pump, that jumper up above that we talked about, it enables the O terminal or the reversing valve for cooling input. This is an orange wire. And so we want to make sure that from the thermostat we come down and tie onto the orange wire for the reversing valve on our air handler control board, and then take it outside to the orange wire outside for our reversing valve. So remember, team, we always energize our reversing valve on our champion product on the O terminal for cooling. Next to the O terminal is a purple dehumidification wire. Now remember, if we're going to utilize this circuitry, this purple wire, we have to have a humidifier. This is a humidifier input. It's also a dehumidification input for cooling, and it's a purple wire. And so remember, team, if we have that jumper up above that we talked about earlier, that hum stat, yes, no, if it's in the yes position, we want to make sure we have a humidistat hooked up to this purple wire, because what it will do in the heating mode of operation, it will allow us to have a humidifier output. In addition, in the cooling mode of operation, it will actually slow the fan down. If it's humid in the house, it'll slow the fan down to 85%. And then once the house dries out, the humidistat will close electrically and provide 24 volts on this purple wire and allow the fan to go to full speed in cooling mode. So it's a dehumidification cooling mode and humidification in heating mode. Now remember, team, to enable that purple hum wire that we're looking at right now on our PowerPoint, we have to have that jumper up above in the yes position. If the hum stat jumper up above is in the no position, it ignores that purple wire and terminal. Right next to the hum and purple wire, we have a blue wire, and that's our 24 volt common terminal, 24 volt common. So if you select to use if you choose to use, or the contractor chooses to use, a conventional 24 volt thermostat, a wiring configuration, these are the wires, and the pigtails are the terminals that will be used. And remember, team, it'll be harnessed in from the factory with about 6 to 8 inches of pigtail wires for the contractor to hook the air handler up to. Okay, want to thank everybody for your attendance today. This concludes Module 1 and 2 for our heat pump diagnostic modules. And at this time, of course, if we had a live session, we would take final questions or comments. But because this is a recorded only session, by all means, if you do have questions or comments, please call me or talk to one of our team members with our Johnson Controls team members, and we'll be glad to answer those questions for you. And again, thank you very much for your attention today on our recorded session 1 and 2 heat pump diagnostic modules.